Hello everyone, my name is Lin Feng Qi. I would like to introduce our work of motion information propagation for neural video compression. The contributions of our works can be summarized as follows. We are the first to introduce bidirectional information interactions between motion coding and frame coding, which assist to achieve the synergy between them. Our motion information propagation not only mitigates the alignment errors, but also saves the bit cost for motion coding. With the propagated features, long-range motion information is implicitly utilized, leading to a better rate distortion trade-off. We propose a hybrid context generation module, which not only strengthens the multi-scale context feature mining, but also provides better motion condition for motion information propagation. Compared with the previous SOTA neural video codec, our method achieves 12.9% bit rate saving, which demonstrates the effectiveness of our method. Compared with previous methods, besides the propagation for frame coding, our method introduces bidirectional information interactions between motion coding and frame coding. And it enables propagation for motion coding through the interactions. The bidirectional information flow can be described as follows. One flow is from motion coding to context generation, and then to frame coding. Another is from frame coding to context generation, and then to motion coding. Through such interactions, feature propagation on motion coding is implicitly built, strengthening the capacity of exploiting long-range temporal correlation. This figure illustrates our proposed motion information propagation. Motion encoder and decoder are in the left while a part of the context generation is in the right. The bidirectional interactions are highlighted as the blue arrow and the red arrow. The high-dimension motion feature GT from the motion decoder serves as motion guidance to mitigate the alignment errors. Meanwhile, besides assisting frame coding at the current time step, the feature HT will be propagated as motion condition when coding the subsequent motion latent. With the propagated features, long-range motion information is implicitly utilized. The bidirectional information interactions can also assist to achieve the synergy between motion coding and frame coding, leading to a better road trade-off. Another advance of DCVCMIP is the hybrid context generation. There are various types of motion in the video, from simple camera motion to sophisticated human activities. For the high-resolution context feature, we adopt offset diversity, which predicts multiple offsets and masks to get more accurate feature alignment and enhance the reconstruction details. For the low-resolution context feature, we apply transformer to enlarge the receptive field and captures better correlation to refine the context. This module not only strengthens the multi-scale context feature mining, but also provides better motion condition for motion information propagation. We investigate the influence of motion condition and motion guidance on motion coding. The top row shows the pixel-level bit allocation for coding the motion latent. It can seem that introducing motion condition not only brings bit rate saving for motion coding, but also leads to a better bit allocation. More bits are allocated for objects in the foreground with larger motion and fewer bits are allocated for the background with smaller motion. When motion condition and motion guidance are both introduced, such effect is more obvious. That is because the complete interaction cycle can enable the more effective feature propagation on motion coding, which can better exploit long-range temporal correlation. We also use cosine similarity to measure the correlation between the propagated feature and the feature from the motion encoder. It can provide some information to help understand why our method is able to save the bit cost and make the bit allocation more reasonable. Here are the BD rate results for PSNR in comparison with VTM 13.2. The negative number indicates bit rate saving while the positive number indicates bit rate increase. As shown in the table, compared with the previous SOTA neural video codec, our DCVCMIP gets obvious bit rate saving, which demonstrates the effectiveness of our method. We also illustrates the road curves here for a better visualization. Thanks for listening. Welcome to see our paper for more details.